I don't know. These are not my slides, so I don't know what's going to happen here. It seems I don't even know what program was used to make these slides. This is how ancient I've become. I tried to figure it out, but it's just kind of doing it. I think the best would be if there was a little stick figure of me and then a voice would just come up, and then I could just stand here and point at it. It would be fine. Yeah, this is, I don't know why, what's this play, what's going on here? Slideshow? Let's get out of this. Let's go to full screen. Maybe that's more, yes, that's less artificial intelligence. So this was one of my grad students who is, she's closer to graduating than she's ever been. I don't know. Near the end. So this is a talk that she gave about her work and so on. But I'm going to focus on this section here, slides 22 through 50 or so, 55. I don't know. But just one of her main topics is things about using new or modern interferometer controls or controls concepts to improve the sensitivity of the interferometers. And this has been sort of bubbling up, and I think this whole push in this direction has been coming from two fronts. One is the efforts to try to model how to do subtraction of this Newtonian gravity noise, and then the other one has been trying to figure out how to handle the very complicated multi-input-output suspension systems that we have. Quadruple suspension, it is quadruple suspension, but you also remember it has a reaction chain. So as you go down the chain, you push off of this back chain. So it's kind of like it's almost two quadruple suspensions, and then you have to still control the whole thing. It's kind of complicated. So to do that, people have been thinking of new techniques. And so I think I won't go through the whole thing, but I'll try to quickly move through it because there are some nice graphics and ideas. Okay. So one of the first things we did was noise cancellation, which uses the concept of feed forward. And in some later slides, I'll show you something about the Newtonian gravity part, but it's difficult at all to measure the influence of fluctuating Newtonian gravity. You have to have a system which is sensitive to displacements of 10 to the minus 19 meters at 10 hertz. But I mean, the correct equivalent thing is something more like acceleration. So whatever that acceleration amounts to. So instead, we thought it would be a nice simulation to do this on seismic noise, just because it's a thing that it's easy to measure. And then this started out as an undergraduate project just to get it going. It turned out to be very useful, and then it turned out to save us during the last science run. So it was something like approximately 4 or 5 year development cycle from just the thought, an undergrad summer project, and then some grad students working on it, and then actual implementation. So what is actually going on? Of course, we have. Oh, wow! This laser has lost its juice, like me. Switch it on. Yes. Lasers, complicated. So this is what's going on. There's motion of the ground. It goes through some sort of system and shakes this pendulum. And what are some things we can do? This blue box represents this hydraulic pre-isolator that I described before, but it can be any system that you have, active platform, which this is holding. And there are two ways to do it. You can put a sensor on this platform and then have some filter which pushes back on this thing, and then you try to minimize the motion of this. Or you can have a sensor on the ground, put it through some control system, and also drive this. And what are advantages or disadvantages of those things? This is the diagrammatic view of these things. Basically, in the feedback sense, if something happens like temperature changes and some mechanical resonant frequency changes by a few percent, there's no effect really on the cancellation that you get. The cancellation is just depending upon having a kind of stable servo and roughly the kind of gain that you need. The trouble with it is if you have a system where the plant that you're trying to control has a lot of effectively time lag because it's a multi-order resonant system, it's difficult to build a compensator which can take care of that. And in some cases it's basically impossible. If you have a bunch of effective time lag, which is coming from a bunch of high frequency resonances that you can invert, then this is something you won't be able to do cancellation at high frequencies. You're kind of limited by the total closed loop dynamics that you can achieve between plant and compensator. For feed forward, this is not an issue. The ground noise enters in here, and so in as much as you can measure the ground noise accurately, you can construct a filter that can do this. And it's never going to be impossible to do because the ground noise always has to travel through here in a causal manner. And the downside is if you want to get cancellation of factor of 100, that means you have to be modeling your system to within 1%. And getting a 10% measurement of your system is pretty trivial. Getting 1% is very hard. I'll remind you. I say remind you, but this is something like I didn't. It's a basic statistics principle, but I didn't realize until recently. When you ask, when I make a measurement of the transfer function of my system, what's the actual statistical uncertainty on each data point? You can look this up in the statistics book. It's quite a lot of measurement excitation you need, or quite a lot of measurement time to be able to do that good. So it's challenging, and so that's why people like to use feedback. However, we ended up using feed forward, and why do we do that? Well, we do it because if you remember these pictures of the initial LIGO stacks that Peter showed you, it's a lot of stuff in there, all these springs, systems going on. And by the time you get to frequencies like 10 hertz or so, the phase delay that you see is tremendous. It's as if it's a 15th order system, so it's kind of anomalous. We see a lot more phase lag than you normally would expect. So the idea of putting a sensor at the bottom of that stack and wrapping a loop where the plant is the whole stack is almost impossible. It's not really, because there's no time travel going on. It's a causal system. The second point, I think, which maybe it's clear from, yeah, it's clear from this. If you remember the feedback algebra that we were looking at yesterday, at each point where there's a sensor, not only are you measuring ground noise, but you're also measuring the noise of the sensor. And for these, the highest class things, maybe the noise at 10 hertz would be something like 10 to the minus 13 or 14 meters. Well, here you do this and you try to cancel the ground noise, and in addition to the best that you could do is, let's say, perfectly cancel the ground noise at 10 hertz. And at that point, you would be injecting noise of 10 to the minus 14 at this point before this isolation system. And the ground noise at 10 hertz, let's say, is maybe 10 to the minus 11 or 12. So in principle, you could achieve a factor of 100 suppression. However, if you did the same thing here, and you were putting your sensor after several stages of vibration isolation, you would be ruining all of this passive isolation that you were already getting. Let me just say that in a different way. Yes?
System, the noise will be suppressed by the gain factor 1 minus G or something.
No. That's not the point I'm making.
And in the feed forward, it will be totally cancelled for all frequencies.
No. Yeah, I mean, this is a similar effect, but I'm just trying to make some different point, which is about where the sensor noise comes into the system. in this diagram, the sensor noise is added to the, in the feed-forward case, the sensor noise is added to the system before the passive filter, before the passive seismic isolation. And in this feedback system, because what you're trying to do is null the electronic signal at this point, the sensor noise is added after the passive filtering. So if your passive filter has already reduced the noise to extremely low levels, and you turn on this feedback system with a conventional sensor like this, the best that you can do is get it to this level of the sensor noise. So in the limit of perfect everything, in one case you'll have, it'll just be like this. Let me draw it to make it more clear. This is the ground. This is our stack. So let's say the sensor is here, and I have some actuator that doesn't matter. Let's say I'm pushing at this point. So I make a feedback loop which looks like this. In this case, if this feedback loop has high gain, and I ask, what's the motion of this thing, x top? Because the sensor noise is added at this point, the best that I can do is that x top will be equal to sensor noise, because that, the feedback loop doesn't know anything special about the noise. It can only suppress to the noise level. On the other hand, if I break this thing and I remove this and put the sensor down here, then when I drive into here, the sensor noise, there's no zeroing to this thing. What the signal is that goes into here is going to be the apparent ground plus the sensor noise. And then when I ask what's x top going to be, if I get perfect subtraction, x top is going to be this noise, but then multiplied by the h of the seismic stack. And as long as this is a reasonable low-pass filter, I win somewhat because this sensor noise will be filtered out by the stack. And we have no hope to be able to do. Yeah, I don't want to belabor it too much, but the main point is that we can never do as good as what we would get at the top of this stack naturally at high frequencies. So this filtering is useful. It's not a general point about feed forward, it's just this specific case. So there are a couple of papers I think that are maybe interesting of some examples of this. In this one, we implemented this active noise cancellation by doing feed forward, but we did it both statically and adaptively. So there was we did this idea of a fixed feedback, fixed feed forward, where we calculated a filter, put it in, and then saw that the subtraction was good and said fine. And in order to see what we could do about tracking plant variations, we also implemented this LMS filter, the least mean squares, which is one of the most simple adaptive feed forward schemes, although we tweaked it a little bit. Some time after that, it turned out that we had a lot of troubles with the operation of the LIGO interferometers in the last science run, and it was because of a lot of low frequency seismic motion. So we implemented, during the middle of the science run, a new control system which would allow the taking of the, well, let me show you the diagram. We took the sensor signals from several points within the interferometer, combined them digitally somewhere around here, and then sent them back to move the isolation systems for all of these. So we did a full multi-input, multi-output feed forward, but static. So to do it statically, we had to measure these transfer functions exceedingly well because we weren't yet ready to implement an adaptive system. But the static system worked well, and we got some nice suppression. So this is showing the power recycling cavity, so the symmetric cavity which is in the central part with this feed forward on and off. This brown trace is showing you the motion of the floor. This black trace is what we were getting using the existing active seismic isolation system. So that was basically already doing this feed forward noise cancellation, but doing it on a tank by tank basis. So each system was isolated by itself. Then we took all of the data together and constructed a Wiener filter to optimize some sort of frequency weighted cost function, which we basically made up, implemented that and got this factor of several more suppression in this critical microseismic band. And that improved the data tremendously. Yeah, some more details. Yes. So let me describe this a little bit. I think this. And this one? No, that's 6. No, this is 6, not 60. Yeah. Yeah, that's interesting. It has.
But what is that signal?
What is that signal? Maybe I have a diagram I can show you. I don't. It's a. These are the kinds of LIGO trivia that you can only get from a few people who maintain this kind of trivial knowledge. There's a mode of the stack where you basically the whole, it's 4 legs and with springs on the whole thing. So when the whole thing twists, if your suspension is slightly off center from the top, then this twisting mode couples into apparent longitudinal motion. And this it's so bad. It's as you can see, the resonance is so big that the top of the stack is moving more than the ground at this frequency. Several years from now, you all will also have this kind of collection of tidbits of what this resonance is and that. So this is just a one-slide description of how the adaptive system works. It may look a little obtuse from this formulation, but if you give me a few seconds, I think you'll see it's not so bad. So what do we have? What does feed forward look like? How to do this? Yeah, I'm not sure what diagram to show really. Let's go back to this description. No, this is fine. So the actuation that we're applying is at these points ahead of this complicated soft system. But the ground motion as it travels from this seismic sensor up through these blue steel piers up into this system has some sort of transfer function. And that depends on some details of exactly where it's placed relative to this thing. And then, of course, it gets more complicated as we introduce more sensors. And we may have one close by, and we may have one which is 4 kilometers away. And there's still some correlation between those things which are separated. And we'd like to calculate what's the optimal filter that, how can we recombine all of these sensor signals to best predict what's the motion of here. And in addition to predicting the motion, we also have to take into account the fact that the actuator itself has some transfer function, which is maybe hard to model. And so what we do is we make an initial guess, which is 0. We say, let's say we don't know anything, so the filter which connects the sensor to the actuator is just 0. And then basically what we do is gradient descent, and we just say, let's take this impulse response, which Peter was showing you, which is equivalent to the transfer function, and we're making a digital filter, which is a estimate of this impulse response, and we sit there and twiddle all of the coefficients of this impulse response. So we're in real time, we're convolving this impulse response with the input data stream, which is the seismometer, and we move one of the, the first sample up a little bit, move it down, move the second one up, move it down, and look to see how it affects the end cost function which we're trying to minimize. And that cost function which we're trying to minimize is the difference between the true motion and our estimated motion. Or in other words, in our case, it's actually just the interferometer's displacement signal. So we're trying to minimize this displacement signal. And at first you may think, this sounds like it's never going to work. If I have an impulse response which is several seconds long and I'm using a digital system, this is something, it could be thousands of coefficients that I'm twiddling all the time. And how do I know that this is not a coupled problem or so on? As it turns out, if you're using this impulse response method, each of these coefficients is independent of the others. So you move one, it's a purely well-conditioned gradient descent problem. There's almost no chance of instability unless you get very aggressive and exceed the built-in time delays in the system. So what's this formula saying? This is saying that my impulse response filter, which it says vector of filter weights, but really means the shape of my impulse response waveform. At time n plus 1 is equal to the previous one plus this thing which encodes the whole adaptation. And this mu is the step size, so it's something like the adaptation gain. This E is the residual error signal, so once we hit our target and everything is working fine, this term sort of goes to 0 and don't have to worry about it. And then X is the waveform, the seismometer waveform. So on each iteration, we take a sample of the sensor, we multiply it by some small number, and we add it to the previous impulse response. And so we use that as our guess for how to update the impulse response.
Minus 2.
This thing? 1 minus tau? Yeah, what's your guess? You've been working on this for a very long time.
Is it due to some delay?
Not delay.
If you have some transient event. If you have some transient event.
Yeah, but exactly, it's for dealing with transients. But
That term doesn't come in normal LMS algorithm. So
that's right. So I mean, if I set this to 0, what would happen?
cannot account for the phase delay due to some transient events.
Yeah, this is the decay term here. This is called, I don't know, maybe this is our own name for it. Leaky normalized filtered X LMS. I think if you look in the literature, usually you'll see stuff like normalized LMS, filtered X LMS, or leaky normalized filtered X LMS. And here we've just put all possible LMS things together. And so the signals are normalized. This is basically that you have a transient, somebody walks by the system and then goes away and the seismometer gets the big bump. If it's a big signal, you don't want that to pollute your estimate of the filter for a very long time. So you'd like it some few minutes or something for that to go away. And you really only want this thing to handle something that happens on very long time scales instead. And so as you increase this tau, you will get more and more decay time. There's a lot more details to this. There's a lot more work that needs to be done on this, because what we really need to know is, for a single input, single output system, it's kind of easy to simulate this. But what we need to do is have real simulations which include the sensor noise, the expected correlation between all of the sensors, and then try some different combinations of these algorithms. This may not be the best one. And what we'd like to do is get something where we have reasonably fast convergence, like less than 10 minutes, but then also pretty good absolute convergence, that we get to the Wiener optimum within less than half hour or something. So if you're interested, you can talk with me. There's an endless supply of simulation problems having to do with this. So we implemented the adaptive one at the prototype at Caltech, and we have this type of improvement at around 1 hertz in the input mode cleaner, which is a 10-meter Fabry-Perot cavity, and then also something like an order of magnitude on the 40-meter arms. And you can see there's almost no noise pollution at higher frequencies. So even though the system is sitting there and the coefficients are fluttering back and forth, because we've put in a slow mu, the step is quite small, the chance for reintroduction of high frequency noise is low. Let's see. Let's show you something else. Yeah, let me just quickly go through this. So Peter mentioned this thing that this gravity noise is a kind of thing that you can't shield from, which is true. And I don't know who first proposed this, but quite a while ago, 15, 20 years ago at least, somebody, maybe Giancarlo Cella in Virgo, maybe? I don't know. His is the first slides that I saw about it, but said, why not just populate the entire field with a bunch of accelerometers, and if we can measure the motion of all of the dirt within the closest several hundred meters, and we have a very sophisticated model of the system, we should be able to subtract out. We should be able to estimate the gravitational noise. Right? I mean, as people say, if you know the motion, if you know the position and motion of all the atoms in the universe, you can rule the world. Right? So that's kind of the concept. First of all, what these guys did is to say, let's survey the motion around the LIGO sites and find out what kind of a limit we will get from this gravitational noise. So there's, this document you can read. It's cited from some paper I'll show you. Let me just describe what these traces are. So this blue one is the expected sensitivity of the advanced LIGO with all of the noise sources included except for this source. And all of these traces have to do with the motion of different pieces of equipment or walls or something in the nearby area. So we can start from what's worth talking about. Acoustics is something that people are often interested in, that if you forget about the ground motion, how much does all this wind matter? Sound within the building matters, and you can use microphones, measure that, and then use this formula, which is just really Newtonian gravity formula, and estimate the influence on the test mass. For usual sound levels, when no one's doing anything dramatic, it's orders of magnitude below. The motion of the building itself has some resonances. That can be substantial, but the walls are not heavy enough for it to be really a problem. We worried also about turbulence on as the wind passes around the corners of the building, but that also directly shakes the building, and that's its main coupling term, so it's compensated for here. The main coupling, as it turns out, is really from really the surface waves on the ground, really just the real ground motion. And so they made a seismic array close to the building and measured this and tried to use this data to see what it would be. So it looks like this source will be a limit for LIGO in this 20 to 10 hertz band, and so something has to be done about it if we'd like to get to the ultimate quantum limits. So let me, so I can move on to a different topic. The punchline is we use the same technique that I just described for seismic noise cancellation, but use it for this. And so we have a simulation where we have all of the seismic waves traveling around, move the sensors around, and look to see what's the optimal sensor placement for each number of sensors, 5, 10, 20, 50, and see how much subtraction we can get. And it looks like, theoretically anyway, we should be able to get huge subtraction, sort of several orders of magnitude in this frequency range. I doubt that this is really true, but anyways, this is the prediction. This is the prediction of the simulation, even including sensor noise and finite correlation, as much reality as we know how to do. So, I think it's up to us now to find out, why this is not true. It seems unlikely we could get 10 to the 5 subtraction.
Right.
lower, you bottom out on the track.
Yeah, of course we have to measure them. So the idea is that for each of these sources which are significant, we directly put a sensor on that source. So for, fans, that's not hard. We put an accelerometer on a fan and so on. For the walls, we have to instrument them. I think we would not, I hope we never get to this point where we're using infrasound detectors. Okay, anyway, so that's that. I just wanted to describe now a couple of techniques for the future controls work that we have going on. And these all fall into these two topics. I don't know if they're really interchangeable. Modern controls, I think, should include everything past basically by hand pull placement. And so that's all the more kind of optimal techniques. And then machine learning techniques we really have not gotten into yet. We read papers if you're very optimistic. So it's totally yet to be done. So what is the state space description? Like Peter was saying, it's a time domain approach. If you have a very high order system, you represent it as a series of first order differential equations. And this is basically it. You often see people talking about the A, B, C, D matrices of the state space. Here, X is the state vector describing the system, so it could be, X could be the velocity of your harmonic, your motion of your harmonic oscillator. It's working. Oh, I was using both. Feel more important people. So anyway, so you can see what these things. Oh yeah, X is the state vector. So, for example, the first element of the state vector may be the position. The second element may be the velocity. Third one may be acceleration, and so on. And you're free to construct as many of these pairs of first order differential equations as you want. So instead of just representing the dynamics of the system, you can also just make up some hypothetical variables like this funny combination of acceleration, velocity, displacement. And using this, you can construct any complicated filter that you need to. Maybe you'd like to have a state variable, which is something like just a bandpassed version of the acceleration of the system or something like that. So you can make a variable which is just that. And then there are these relations which allow you to transform from the state space representation into your usual open loop gain, and et cetera. And you can go back and forth. So fine, but there's still the so what question. Why is that useful? Many modern techniques for doing optimal and adaptive control use the state space representation. I would say the most simple optimal controller that we know about is this so-called linear quadratic regulator or linear quadratic Gaussian estimation. Here, this is a kind of cost function that you're trying to minimize, J, and this is giving you this X is sort of the error signals of your system. So again, the state variables, displacement, velocity, and so on. And this Q is a matrix which is relating these terms together. So in the simple case where you're just trying to minimize the RMS velocity, for example, you would just have a vector which would show you displacement, velocity, and so on, and then your matrix here would just have a unity element for the velocity times velocity term. So the 2 term would be 1, and everything else would be 0. And then this integral would be an integral of velocity squared. Here, this is the same thing, but for your actuation variable. So if you'd like to minimize the energy consumed by your system, or you'd like to make sure that you're not saturating your controller, you can put some sort of weight on similarly on the actuation. And by expanding your state and having many derivatives of the actuation, you can also have some complicated frequency-dependent weighting on these things. So you do this, you can form this kind of cost function. It's a quadratic cost function. And there are many, many commercial software packages out there for solving this, this Riccati equation, which tells you basically how to find the correct controller that gives you an extremum for this, or where the derivative is 0 with respect to the coefficients. Yeah, I don't want to go into these details, but they're beyond the simple LQR techniques. There are more advanced techniques. I would say H infinity is one of the, ignoring the issues about margin and stability and so on, H infinity is one of the maybe most popular ways to make a optimal controller. There you make just a more generic cost function which can take into account the largest eigenvalues of your system or some weighted determinant of the state variables of the system. But essentially it's acting like you'd expect it. You give it something like this, or in the H infinity case, you define it slightly different, but you write down a cost function for your system where you say, well, I really care about the fluctuation here at 1 hertz and not so much at 10 hertz, and it's really important that I don't put back any drive into the system in the 30 to 50 hertz regime. And you can write them all down formally. So you put all of the wisdom that you have about the system into the cost function for your H infinity once you've created the state space correctly. And then you just use one of these commercial packages like MATLAB or something like that. It solves the H infinity problem for you and just gives you the controller. And there's really nothing to it. It's extremely fast. And what I found is that using this technique, basically what you find is your own ignorance is revealed to you. You do it, and then you can get a Bodhi plot of the system, and then you look at it and say, that's just not what I would have done by hand. And sometimes that's good, sometimes that's bad. If it's it always really does what you ask it to, but then you just find, well, I didn't really ask it to do the right thing. But what's the advantage of that? If all it can do is just do what you've asked it to do, then it seems like it's kind of useless to use these more modern techniques. But it's not so. I mean, in fact, when you're doing the controls for something like 300 seismic loops, you don't want to have to redefine your wisdom each time. You have a general wisdom which should work for all of them. And they all may have differences in the plant parameters or the noise inputs or something like that, but once you've put in what's important in terms of gravitational wave sensitivity, this algorithm can just generate the controller for each one of them. So we are not yet doing this, but I think it's a promising direction to go to. And there's other stuff. This H infinity technique is some decades old at least. It's possible that what we'd like to have is not a continuous cost, but some sort of more sigmoidal or nonlinear activation function. Once you reduce the motion of your system to below some level, you kind of don't care anymore. It's sort of speckmanship at that point. If all you need to do is make the cavity motion be less than 1 picometer to have it be linear, if you get 1/100th of a picometer, you can brag to your friends, but nature doesn't care at that point. So rather than have quadratic ones, you can use neural networks maybe to have a more nonlinear one. Do I have time? What's the time? I'd like to then, there's this Tobin Fricke, who's a postdoc at the AEI, has made a nice set of slides for introduction to state space methods. So this is all out there, but he's kind of related it to what's. This is back? You want me to switch? You don't like this? Okay. So in this presentation, he talks about what's the point of using the state space approach, and then also something about state estimation, which is an interesting technique. So he says, yeah, here's this transfer function that you're used to, and how do we talk about it in the state space? So we flip back and forth a little bit and see, yeah, here are the command inputs to your system, and here are the outputs. And in the time domain, of course, you can write down the same thing, and this state matrix occupies the same function. So here, this state input is related to these outputs just by the integral, so because they're first-order differential equations, and the dynamics are encoded in all these ABCDs. So what are these things? C is sort of telling you about the transfer function that relates your state to the measured variables that you have. So you can say things in here like, my sensor is only good within this narrow band, or it can encode things like that. D is something like a feed-forward thing. So it's if you put in a signal and it directly affects the output with almost no transfer function, this can be in there. And then these are, as you can see. So this is a nice example. I think yesterday, well, all week maybe we've been talking about the harmonic oscillator, and this tells you how to set up the state space matrices for the harmonic oscillator. So in the differential equation, we start off like this. These are the external forces acting on the system, and here's the A matrix. So let's see if this makes any sense. This says velocity is equal to velocity. Okay, that's good. And it says acceleration is equal to kx over m and minus gamma x dot over m. So that looks good. If we divide through by m, that's what we expect. So just these elements of the differential equation have shown up in here. What about these things? Does this B matrix make any sense? This is saying that if I put in an external force, it doesn't directly affect the velocity. But if I take the external force, divide by mass, that's my acceleration. That's good. It's logical. So far, everything is going according to Newton's laws. We should feel happy about this. So still, I think this hasn't answered the so what problem. Why would we represent things like this instead of just using transfer functions? It's a little. I think this. Most everyone who's used to this Laplace domain controls says the same thing. I think this is a nice example of why we might like to do that. So what's going on in here? There's a system. You put in inputs, dynamics happen, and you get some outputs. But in the real world, we're not able to measure all of the internal states of a system. Maybe we're trying to control the temperature of one of these optics using some external heaters. And all that we can measure is something like what's the distortion of the surface, or very roughly we can measure the temperature using some kind of remote thermometer system. But we'd like to know what's the internal temperature distribution or something like that. What this does is it's a little similar to this gradient descent technique I was talking about for feed forward, but instead it's something like a feedback technique to get feedback technique on the internal states of the system. And what it's really doing, if you look carefully, is it's not actually using the direct measured outputs of your system to make the feedback, but instead there's a model of your system, and your feedback controller is taking the estimate of all the internal states to make the feedback to your system. So it's saying, based on these noisy sensor outputs of my system, I can take the output of my simulation, subtract it from my real ones, make a filter here that removes some of this noisiness that's unpleasant to me, and I can feedback and update my simulation. So I can make my simulation track my real world device, and I can do it with the kind of frequency response I care about. And now I can take this estimated system, which I have full knowledge of, and then I can make some more intelligent feedback system. I don't know. It's just read. These are not my slides. Yeah. What is that? Maybe that's command input. Yeah, noise or where you want the system to move. But this, I think this is often the situation with us. We have a limited number of sensors, and we'd like to be controlling something else. We're always trying to make some imperfect estimation of that, and this estimation scheme is a nice way to do it. So anyway, that's all I have. I wanted to say, I have a web page which I wanted to show you about like the really big open problems and control systems work for really the gravity wave field. But over the Christmas break, the RAID hard drive which handles this computer has failed. And even this morning, it was dead, and it's impossible to get anybody to come in and fix your computer over Christmas. Anyway, I will send around the link, and once I get back, I can fix the RAID myself, and then you can look at it. But if the web page was displayed here, what you would see, a list of something like 10 or 15 problems, and basically the point is we're just getting into this realm of trying to use more sophisticated control system techniques to improve the performance of the interferometers, and we don't really have a concrete statement to say, yes, this is going to be the greatest thing ever and give us big improvements, or it's all played out and there's nothing to be done. We think there's a lot of promise in this area, but it's very unplowed. So there's a lot of room for people to come in and make contributions.
Take the output of K and feed it back into the feedback loop inside the simulation. But that feedback, is it actually in the time varying parameters, or is it actually going to the ABCD?
It is going to the ABCD. Yeah. This is something like that. Yeah, you know, when this thing matches this thing,
The difference
this one will be 0. So hopefully in normal operation, this loop is not really doing anything. And this is active. You know, for our suspension, well, you know, there's many parts of the system that are invisible to us, and the sensor that we have is several layers out. We would rather be controlling the variable of interest.
One of the plots you showed earlier, there's a peak in 6 hertz.
Yes.
So that comes only when you switch on the control system?
No, it's part of this passive stack. We did mechanical resonance.
But it did come up when we turned on.
Is that true?
Yeah.
I think it's there.
It's ground.
And it's both in the black and the red. Yeah, it's true. The ground is not so noisy, but it's the fault of the. It's this. Yeah. I will complain more about this stack after lunch.
I have 2 questions. One, is there any difference in the frequency response and the phase delay response of feedback and feed-forward systems, or are they same?
Yeah, they're different.
They are different.
Yeah.
Can you schematically show what is a typical trend in these 2 systems? How they differ? Pictorially, that frequency response, like for example, in the feedback system, there is a 180-degree flip above and below the resonance in the phase angle, and the frequency response falls at the rate of 20 dB per decade. Typical response. So,
Yes.
are they same for the feed forward also?
No. There's also something which is important, which is the feedback gain you have when you're doing adaptive feed forward. So there's a feedback loop in the adaptive feed forward, and that has a phase delay which has to do with, I'm not sure how to describe it. I can do something on the board later for you.
Okay.
But in the basic static feed forward, there is no phase delay to worry about. Except for technical things having to do with the fact that we don't know how to make an electronic system fast enough. But for all of this low frequency kinds of things, that it's not important.
The second question is related to, can a feed forward system result in accidental resonances?
I don't think so. Usually the worst that happens is you turn it on and the sign is wrong, or something
Yes,
like that.
the phase angle can be wrong at
Yeah,
some
when it's
frequency.
completely wrong like that, the worst that happens is that the noise increases by a factor of 2. So, bad, but in the feedback case, when you make that mistake, you can have real damage going on. Feed forward is kind of mild.
When you use static noise cancellation, if the performance change over time, it must, I would expect it to change over time, unless you're updating those filters regularly.
Yes, there's a plot in here about this. Have you not read all of my papers?
Not with that detail.
Not with that detail. What are you doing with all your time? This is fascinating reading. We went to great pains to make this plot. Exactly the question that you asked. We were predicting your question. Yeah. We put in, yeah, this was the worry. We did it in simulation and then also in reality, which is we let the adaptive system adapt for a couple of hours and then froze it by changing the adaptation gain to 0, and then let it run for something like 1 week, and then look to see what the variation was. And it's tiny, very surprising. There's occasional bursts of noise where something clearly is going on, but otherwise it's not changing that much. And then that's in this tiny prototype. Then we did the same thing here. There's some plots that Ryan Garosa made, where these filters were made in sort of January or February 2010, I think. And then he looks at the performance for several months, and with the idea that he was going to update them, but then just never bothered because the variation in the physical system is all it implies for this seismic cancellation is that on average the location of seismic sources is not changing that much. Of course, occasionally something happens, like if a really heavy car drives by, then. But let's look at the plot.
Yeah, so that's